Rates part 2. So let's solve these questions. A road perpendicular to the highway leads to a farmhouse located 1 mile away. So here's a farmhouse. An automobile travels past the farmhouse at a speed of 60 miles per hour. How fast is the distance between the automobile and the farmhouse increasing when the automobile is 3 miles past the intersection on the highway? So a lot of things going on, right? We kicked it up a notch. So we have a farmhouse that's located 1 mile away. So this right here that's a fancy one. This is 1 mile away. That's not changing. So that's actually a constant, right? That's always gonna be 1 mile away from the road. So that's a 1. Now these two things we don't know. So we'll put some variables. We'll put x and then we'll put z. Usually have y be the vertical and x be the horizontal, and then the diagonal be z. My y this time is just 1. So that's the way it is. So what else do they tell us? An automobile travels past a farmhouse at a speed of 60 miles per hour. So they're saying this rate right here is 60 miles per hour. Now remember, this is x. The rate would be dx dt. So 60 miles per hour dx dt. How fast is this between the automobile and the farmhouse increasing when the automobile is 3 miles past the intersection? So we want to know how fast is this thing increasing. Now you might get confused. It says how fast the distance. So it's not z, it's how fast. It's the rate at which z is increasing. So we're actually looking for dz dt. Look what it says. When the automobile is 3 miles past the intersection. So when x is 3, of all things. Right, so when this guy is 3 miles past the intersection, we want to know this. So this is what we have. That's all they told us. So we know this is 1, we know this is x, that's z, that this rate here is 60 miles per hour. We want to know how fast this thing's increasing when this guy is exactly 3 miles away. So like all related rates questions, how do we relate all this? Is there an equation that relates this type of triangle? There's a few, but specifically here, since we're talking about the hypotenuse, we want to talk about x squared plus y squared equals z squared. Right? The Pythagorean theorem. And one thing here, it's an ugly z, I know. That's not a y now, because I know it's a constant. This actually doesn't change, so I could plug that in. So it's x squared plus 1 squared, or just 1, equals z squared. That's our equation. And like we always do, once I get an equation that works, we want to relate it. We got to get dx dt and dz dt, so we got to take a derivative of this guy. And keep in mind, look what happens, right? If I take a derivative of this, I get dx dt. I have that. If I take a derivative of this, I get dz dt. I want that. If I took a derivative of this guy, I would get dy dt, which I don't have anywhere. So that was not going to work. So it's key that you understand this is a constant, so I can actually plug it in. So let's take a derivative with respect to t, like we always do. So derivative of x with respect to t, or x squared, is 2x, but wrong variable, dx dt. Here's the thing, derivative of 1 is 0. A lot of people forget about that. They just put a 1 down here. It's actually 0, it goes away. This side, derivative of that is 2z, wrong variable, dz dt. Like this. Right, now before I plug everything in, look what happened. Let's talk about this. Let's try to plug stuff in, right? If I try to plug stuff in, x, I know what x is going to be. I took a derivative, right? It's 3. dx dt, I know what that is. They gave it to me, 60. Then we get to z, and I don't know what z is. I don't have a value for z anywhere. I'm looking for dz dt, but I need z. So how do I find that? You go back up here. That's an equation that has x and z, and I know what x is now, 3. So at the very specific moment, when this guy is 3 and this guy is 1, I could figure out what z is by doing a squared plus b squared equals c squared. So I get 9, I get 10 equals z squared, so radical 10. So this is going to be rad 10. Right, so let me just simplify that a little bit. This is going to be 6. Actually, if you want, we could make life a little easier, divide everything by, notice I do have a 2, we could get rid of that. So you get, what is that, 180 equals rad 10 dz dt. Then divide by rad 10, get 180 over rad 10 miles per hour. Miles per hour. That's the same thing as this, by the way. The little slash means per. of dz dt. So there we go. That's how fast it's changing when the car is exactly 3 miles away. Right, I can change that to anything I want. If I wanted it exactly 5 miles away, it just changes some of the math around, but it's the same way you solve it. Anyway, so that's our answer. Next one. A canonical tank has a height of 3 meters and a radius of 2 meters at the top. Water flows in at a rate of 2 meters cubed per minute. How fast is the water level rising when it is 2 meters? So let's draw our tank here. It's a cone. Cones are very special. You gotta keep in mind how we do these. So it has a height of 3 meters and a radius of 2 meters at the top. So it's saying that this guy is 3 and that the radius here is 2. I'm not drawing a scale. Water flows in at a rate of 2 meters per minute. So there's water flowing into this tank. So like from up here. I can't draw. There's something dropping water into here. Now the rate at which it's doing that is 2 meters cubed per minute. Notice how I mentioned before, but when water flows in, it's a volume. And if you're not sure, look at the units. So just tell me dV dt equals 2 meters cubed per minute. So dV dt equals that. How fast is the water level rising? So do you remember what the water level is? Water level is this guy. It's not the height of the whole cone, it's just the water in the cone. So that's my h. So the question is, they want is dH dt when it's 2 meters. So how fast is the water level rising when it's 2 meters? So the it here being the water level. So when h is 2, how fast is this guy going up? So there's our given is the given's all this, right? That rate is 2, the whole thing is 3. We're pouring water in at this rate. You want the rate at which the water level is increasing at height being 2. Now to do this, we need an equation that connects all these. So we're talking about volume here, so we need volume of a cone. I've said this before, but volume of everything is just area of the base times height. Except if it's pointy. If it's like this, like if it's a pyramid or a cone, like if it could stab somebody, then it's 1/3 area of the base times height. So that's what's going on. Now here's where it gets a little tricky. Now we generally think, okay, I could find that the 2 and 3 are not changing. I could find that area. Like I could plug this in. But you gotta watch out. What we're talking about here for volume is volume of the water level. We're talking about this guy. And this guy, that has a radius and a height, which we don't know. So my formula here is actually this. Volume equals 1/3 area of the base, which here would be a circle, pi r squared. I don't need the parenthesis. Let's confuse people. Times height. That's my formula. Volume equals 1/3 pi r squared times height. Now, what do we normally do when we see this? We take the derivative. So like, okay, take care of this, I get dV dt. Good, I have that. Over here you have two variables. So, a couple things. First, you would get dr dt, which I don't have anywhere. You would get dH dt, which I do have, but also this would be a product rule because it's two different variables. You have to do the product rule still. Yeah, that still exists. So we join the big issue here is actually the product rule we could do, it's fine, but we don't have the rdt, so that's a problem. So I can't have the RB there because we don't have it. So what do? We have to get rid of it. So this is where this actually comes in handy. We gotta basically get rid of the R and change it to an H. So we gotta find proportions. The R and H here are related by they're similarly proportional to the whole cone. So the radius there would be 2, not the height there would be 3. To recap, right? This cone and this big cone are similar, so we could proportion them out. So the radius of this guy compared to its height is equal to the radius of this big cone to its height. Now, why are we doing this? Because right now I cannot take a derivative of this equation here. An R, and I don't have dr dt, so I cannot take a derivative of that R. So I could get rid of it. So how do we get rid of it? By doing this, by setting up the proportion and then solving for R. So let's get rid of that H there. Multiply both sides by H. You could cross multiply, but this is easier. So you get 2/3 H, or 2H over 3. Same thing. So if this is my R, I could sub it in for the r right here, and that gets rid of the r. So now we have this. Don't forget it's squared. So you get this guy. Now, do I always have to do this? No. If you have drdt, feel free to take the derivative, do the product rule and all the good stuff. But if you don't have a drdt, you have to get rid of the r. Same thing if you didn't have h, you have to get rid of the h. If you didn't have dht, get rid of the h. So we have this. Now, before we take a derivative, let's simplify it a little bit. So the squares will go to both things. So I'm going to get 1/3 pi 4/9 h squared h. So if I simplify that some more, I'm going to get 4/27 pi h cubed. Right, just simplify, just did some algebra, right? So square both of them, square everything inside of here. Now this is 1 times 4 is 4, and 3 times 9 is 27 pi, and then h squared times h is h cubed. And now I can take a derivative, because if I take a derivative of this guy, I'm going to get dv dt, which I have, and I'm going to get dh dt, which is what I want. So let's take a derivative. Derivative of this guy, right? With respect to t. With respect to time, related rates. So derivative v is 1, but wrong variable, dv dt. 4/27 pi h cubed. The only variable here is h. So you bring the 3 down, subtract 1 off. Now when you bring the 3 down, it's 4 times 3/27. 3 and 27 reduced to get me 4/9. Pi h squared. And then don't forget, wrong variable, so dh dt. Alright, so that's how that became this. Bring the 3 down, it goes 3, so you have like 12/27, but you can divide them both by 3, reduce it, and you get this. And now we just plug in what we have, right? dv dt is 2. That's all there. H, remember it wants h at 2, so h is 2 squared, and then dh dt. So, do a little algebra. 2 times 4/9 times pi times 4 dh dt. I get 2 equals 16 pi/9 times dh dt. I'll multiply by the reciprocal here. So multiply both sides by 9/16 pi. Done, 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 done. I get 18 over, so you get 8 is over 1. 18/16 pi. Or if you want to reduce that, divide by 2. 9/8 pi is on the bottom. dh dt. Now, again, if you want units, h. What is h? It's a side. So it's not, remember, you only have a power if it's area or volume. So this would be whatever the side is, meters per minute. And there we go. That's the answer to this cone problem. Yeah, we love cone problems. So we're going to do another one. A cylindrical tank has a height of 3 meters and raised to 2 meters at the top. The water level rises at a rate of 0.3 meters per minute. At what rate is the water flowing in when the water level is 2 meters? So similar type of problem. And we have a water level right here. So the height is 3. The radius is 2. Water level is rising at a rate of, so now keep in mind, so water level, so that's your h. So the h dt equals 0.3 meters per minute. At what rate is water flowing in when the water level is 2 meters? So they want to know what dv dt is when h is 2. So again, here's our water. So if we do a little thing here, there's an r, and this is h. So just like before, okay, we have a volume of a cone. We got to set up the equation for that. So volume equals 1/3 pi r squared times the height. Right, volume of a cone is 1/3 area of the base. Remember, this is my base, not the whole thing. We're talking about the water level. Area of the base pi r squared times the height. Now, just like before, what happens if I take a derivative of this? I get dv dt. Fine. I'll get dr dt. Not good again. I don't have a dr dt anywhere. I would get dh dt, which I need. So I gotta get rid of that r. So just like last time, I gotta get rid of that r. So now we know how to do it. We go, okay, I gotta find my proportion. R over h equal radius here to that. So 2/3 The whole idea is you want to solve for r, so multiply both sides by h, and you get r equals 2/3 h. So there I go. Now I can sub it in. We have the volume equals 1/3 pi. Let me get rid of that parenthesis. Pi, plug it into here. That gets me 4/9 h squared. So I'm going to get 1/3 pi. 4/9 times 1/3, I should do that too. So if I multiply this guy times that guy, I get 4/27, just like we did last time. H cubed, right? Because h squared times h. So we get this again. And now we can take a derivative. Now if I take a derivative, I get dv dt here, and I get dh dt. So now I'm all clear. So let's take a derivative, select the time. And you get dv dt equals, bring this down, subtract 1 off, 4/9 pi h squared. Don't forget dh dt. Most common mistake is people forget like the dh or dr dt or something like that. That is the wrong variable. We have to add that in. Now look, what do we have? We have dh dt is 0.3, and we wanted to find the volume when h was 2. So plug it in 2. So we're gonna get 4/9 times pi times 4 times 0.3 or 3/10. I'll put 3/10. Multiply all that out, and you're gonna get 8/15 pi. Pi is actually on top in this case. Last time it was on the bottom. Again, if you're worried about units, you can do the math on it, or look, it's a volume. So it's going to be cubed, so it'll be meters cubed per minute. And yes, you do need units. So there we go with that one. Okay, let's do a different type of problem. 12. Sonia and Isaac are in motorboats located at the center of a lake. At time t equals 0, Sonia begins traveling south at a speed of 32 miles per hour. At the same time, it takes off heading east at 27 miles per hour. How far are Sonia and Isaac traveled after 12 minutes? 12 minutes is, no, 12 meters is 12 minutes, I can't say meters. 12 minutes is 1/5 of an hour. So let's see what's going on here. We start here, and then these rich people, Sonia and Isaac in their motorboats, center of a lake. At time t equals 0, Sonia begins traveling south, so she goes south at a speed of 32 miles per hour. Like I said before, anytime I go up and down, I like to use y. So let's say this is y, and so her rate is dy dz was 32 miles per hour. Again, it's a rate, so y depth is z, dy dt, sorry. That's how fast she's traveling along the y. Technically, it's probably going negative because she's going south, but we'll leave that for now. At the same time, Isaac travels off heading east at a speed of 27 miles per hour. So he's going this way. So that's my x. That'll be dx dt equals 27 miles per hour. He's going to east, so that's fine. The question is, how far have Sonia and Isaac each traveled in 12 minutes? So we want 12 minutes. So we want to see how far apart have each traveled in 12 minutes. Now, the hint here is it's 12 minutes is 1/5 of an hour. So if we're talking about Isaac here, he's traveled 27 meters. We've only traveled a fifth of how, like we traveled 27 miles per hour, but we've only gone 1/5 of a mile, 1/5 of an hour. So 27 times 1/5 miles. Right? This is miles per hour, and this is 1/5 of an hour. So these cancel, you just get miles. Same thing down here with Sonia. She's traveling at 32 miles per hour, but she's only gone 1/5 of an hour. These cancel, and you get 32/5 miles. So that one's done. At what rate is the distance between them increasing at t equals 12? So now we have to go back to our picture. And we're looking for this. Let's call this z. And the question is, at what rate is it increasing? So what's dz dt at time equals 12? So that's the question there. So I need an equation that puts all these two together. Well, you have a triangle with the x, y, and z. It looks like a right triangle. So this is going to be x squared plus y squared equals z squared. Right? So that's the equation we get. Now, I always want to check when we do this. The next step is generally take the derivative, but make sure it works. So, if I take a derivative of this, right, I'm going to get dx dt. Do I know what that is? I do. I know what dy dz is. I do. dz dt? Yeah, that's what I'm looking for. So it's all good. I can just take a derivative here. So, let's take a derivative. Derivative of that would be 2x, wrong variable, dx dt, plus derivative of y squared would be 2y, wrong variable, dy dt. Derivative of z squared would be 2z, wrong variable, dz dt. Now, we can do one thing to help each other out, right? Notice how they all have a 2 in front. Let's get rid of those 2's. Divided by 2. So we have this. Now, it's been 12 minutes, so let's plug in what we have. So, x here, right? How far have we traveled in 12 minutes? Well, we did it up here. We traveled 27 over 5 miles. So that's my x. What's dx dt is how fast we're traveling, which they told us was 27 miles per hour. Y, same thing. Right, we figured out earlier how much we traveled in 12 minutes, so for y that would be 32 over 5. And then dy dt they told us is 32. Over here we come up with z, and just like we defined like this before, we don't know what z is. That they don't tell us. We didn't find out z at any point, so now we have to find it out, and we want to find it out at 12 minutes. So that has to do with over here. Right, so guess our triangle. We know one of these guys is 27 over 5. Our other guys is 32 over 5. Got to figure out what z is. So Pythagorean theorem. Because again, why these fractions? So we're doing it at 12 minutes, which is what we found out here. So we're going to get this ugly 27 over 5 squared plus 32 over 5 squared. And I'm going to leave it like that because that is disgusting. And that's how the key, that when we use the key, you'll see it like that also. Because we're just going to put it all on our calculator. So that's what this is right here. It's a square root of 32 over 5 plus 27 over 5 times dz dt. And then to solve for dz dt, we just divide by this. We plug that all into our calculator. We're going to get 27 over 5 times 27 plus 32 over 5 times 32 all over square root of 27 over 5 squared plus 32 over 5 squared. If you plug that into your calculator, you're going to get 41.868 miles per hour. And there's the answer. So that's how rate this is increasing. So for every minute, by every hour, it's increasing by about 40 miles. Next one. Oh, these are interesting. A 6-foot man walks away from a 15-foot lamppost at a speed of 3 feet per second. Find the rate at which the shadow is increasing in length. At which his shadow is increasing in length. And that's very important. This is actually super important. His shadow. Because that changes between, is the whole, are we talking about the whole thing, or are we talking about this little part right there? Since it's his shadow, we're only talking about this part. If we're talking about the shadow like from the lamppost, it'll be the whole thing. So this is his shadow. This is the distance from the lamppost. This is how tall the lamppost is. And then we know his height is 6 feet. Now here's the thing about these problems. I'm going to tell you right now. We never use Pythagorean theorem on these because I don't know what this length is here. So in this problem, we're going to set up proportions. We're going to set up this big triangle compared to this small triangle because those two are similar triangles. So the huge triangle and the small triangle are similar. So, but let's talk about what they want. They gave us. So they gave us all this information. They told us a man walking away from a lamppost at a speed of 3 feet per second. So we'd like to make this x and y. Let's separate this. And the speed at which he's walking away from the lamppost is dx dt. And that is 3 feet per second. Find the rate at which his shadow is increasing in length. So they want us to find dy dt. So that's our given, and that's our 1. How do we set up the equation? We do the proportion here. So we're going to do, I like to do this side, y over 6 is equal to, since I did the side over this part, I got to do this whole side, x plus y, over this side, 15. Now normally I say, okay, now let's, if I take a derivative, what happens? We get dy dt. Good, I want that. And we'll get dx dt. Good, I have that. So we're all set. Before we take a derivative, though, let's make this a little nicer. I would cross multiply here. So you get 6 times x plus y equals 15y. Distribute 6x plus 6y equals 15y. Make it a little nicer. Right, so we get that. Now we can take the derivative. Derivative of 6x is just 6, but wrong variable. Derivative of 9y is just 9, but wrong variable. And now we plug in what we have, what we want, right? We have dx dt is 3. And then we have, we're looking for dy dt. So I get 18 equals 9 dy dt. Divide by 9, so I get 2 equals dy dt. Don't forget our units, what are we talking about here? What is y? Y is the distance, feet, and then t is time, seconds. So 2 feet per second. So that's how much his shadow is lengthening, is 2 feet per second. So every second this is getting 2 feet bigger. And that's the setup for this problem. When we have a lamppost type of problem, generally what we do is proportions. So some things we know, some things we don't know. We generally keep this. The thing in front of the person is his shadow, very important, because they might say like the whole length. His shadow is this portion, so keep that in mind. Next one. At a given moment, a plane passes directly above a radar station at an altitude, height above ground, of 6 miles. So if the plane's speed is 500 miles per hour, how fast is the distance between the plane and the station changing half an hour later? So what's going on here is we have a plane. Put plane because I cannot draw. And we have a radio station, a radar station. So at a given moment, a plane passes directly above a radar station. That's like right here. At 6 miles. So keep in mind, that's 6 miles above. That's not going to change. The plane is just going straight across. So that's 6 miles. 6 miles. The plane speed is 500 miles per hour. How fast is this between the plane and the station change half an hour later? So let's do a couple things here. So the plane's going this way. And we're trying to figure out how far apart they are. How fast the distance between them is changing. So this will be my y, this will be my x, this will be my z. What do they tell us? The plane speed is 500 miles per hour. So this guy, dx dt, is 500 miles per hour. What are we looking for? How fast is this between the plane and the station changing? So how fast is this? How fast is dz dt changing at t equals, now we're doing miles per hour, so my hour here will be 1/2. Half an hour later. Right, so we're doing miles per hour, but now we want half an hour later. So 1/2. Still kind of sucks, but not as bad as the 12-minute one we did earlier. Anyway, so we get this. As always, we need to equate these two. So how would I do it? Well, this looks like a right triangle again. So we're going to do x squared plus y squared equals z squared. But keep in mind one thing. One of these guys is a constant. Oh, even before we do that, right? Just look at what they always like to check. If I take a derivative, do we have everything? If I took a derivative of x, dx dt, done. I take a derivative of y, there's no dy dt anywhere. So there's an issue there. We gotta look into that. And you take a derivative of z, you get dz dt, so that's fine. It's only the y one is a problem. So how do we fix that? Well, we notice that this is a constant, right? This is not going to change. That's going to be 6 miles above and it's going straight across. So instead of putting a y there, we can just put a 6 there. Now we can do what we always do. Take a derivative with respect to t. Derivative of x squared is 2x dx dt. Derivative of 6x squared is 0, right? It's a constant. And then over here, derivative of 2z is 2z dz dt. Sorry, I got in my own head there. Like that. Just like always with these, probably cancel out the 2's. So we just have x dx dt equals z dz dt. Do we know what all that is? I actually don't know what x is. So it goes 500 miles per hour, but we're only going for half an hour. So I can do the math there. Since we only traveled half the distance, it's only 250. Right, we're traveling at 500 miles per hour, but it's only been half an hour, so 250, 500. dx dt is 500. That's how fast we're going. On this side, what is z? I don't have z. I gotta find z. So we gotta do a triangle again. Now remember, this triangle is at half an hour. So this is always 6. It's only been half an hour, so that's 250. And that's my z. So z is going to equal the square root of 6 squared plus 250 squared. Definitely need our calculators. I guess we just leave it like that and plug it into the equation. And then we're just going to divide by that. So we're going to have this divided by this guy because we're looking for dz dt. I need some space. Sorry about that. Sorry about the mess. So it's going to be 250 times 500 all over square root of 6 squared plus 250 squared. We sub that into a calculator and we get 499.856 and then miles per hour. So that is how far they are changing. It's about 500 miles per hour they're changing. That's a pretty fast 500 miles per hour. That's how far apart they're getting. Next one. How fast is the distance between the plane and the station changing when the plane passes directly above the station? Ooh. So we have our radio station, we have our plane. Right, this is 6 because we knew that from the beginning. Well, how fast is the distance between the chain? The question is, how fast is the distance between the plane and the rotation changing past the directly above the station? Well, the distance is 6, right? Like that's our distance. And it says how fast? Well, how do you figure how fast it is? Take the derivative. Well, what's the derivative of a constant? 0. So it's 0. When the plane is directly above the radio station, the radar station, the distance is 0. Okay, next one. As a man walks away from a 12-foot lamppost, the tip of his shadow moves twice as fast as he does. So this is what I was talking about earlier. So tip of his shadow is different than his shadow. His shadow is the whole thing. The tip of his shadow is like, let's draw a picture first, right? So here's my lamppost. Here's our person walking. And then here's the tip of his shadow. So when they say that, they mean all of this. So it's a little bit that's changed in the last one. The last one we did, to find the rate at which his shadow. So there's a difference between his shadow and the tip of his shadow. Tip of his shadow implies they want the whole thing, like how far all of this is changing. So that's the tip of his shadow. We do the whole line when it says tip of his shadow. So the tip of his shadow moves twice as fast as he does. What is the man's height? Whew. So let's see what's going on here. So that's 12. The man's height we don't know. Let's say it's x. It's height. Let's make it h. You're gonna see why I make it h instead of x in a second. So what is the man's height? When we do this, so since we're making the whole thing here y. So this whole thing is y. We have to make one of these sides x, and we like to make this side x from here to here, which makes this side y minus x. Right, because we still got to do a proportion. So if this is x, so we make this whole thing y, this is x, how much is this? Well, you just subtract it from this guy. So it's like this is 10, this is 4. How do you find this? Do 10 minus 4 is 6. Same idea. This is y and that's x. Do y minus x, so y minus x. Okay, so how do we solve the problem? We do set up a proportion. We're going to do, like we always do, we do this guy over this guy. So we're going to do y minus x over h. On this side, we're going to do the whole triangle, which would be y over 12. Oh, I just realized I haven't set up our given or want. So let's talk about our given and what we want. So what is the man's height? So that's what we want, the man's height. So just the h here. What's our given? The tip of the shadow moves twice as fast as he does. So the tip of the shadow is dy dt. Well, tip of the shadow is y, but we're talking about the rate here, right? Fast. So dy dt moves twice as fast as he does. So how fast does he move? Like, what's that equation? Remember, it's not so don't remember. It's not dh dt. That's his height. That's how fast his height changes. I'm talking about how fast he moves. That's x. That's him walking away. So that's dx dt. So the tip of the shadow moves twice as fast as he does. So this guy's changing it twice as fast as he's walking away. So that's our given. This is our want. Now here's the key thing about the want here. Is the guy's height. That's not changing. The want is a constant. That's going to become very important right now. So like I always do before we take our derivative, right? Next step here, we take a derivative. Let's look at what happens before I take the derivative. Like, do I have everything I need? So if I take a derivative of y, I'll get dy dt. I have it. If I take a derivative of x, I'll get dx dt. I have it. Same with the y. If you take a derivative of h, like you'll be like, oh, you get dh dt. You don't. H is a constant. It's not a variable like x and y. H is a number. We still know what the number is, right? That's a constant. A variable is something that changes. This is changing amount depends how fast he's walking or how far he's changing. Like, this is a constantly changing thing. H is not. H is a constant. We just don't know what the value of that constant is. So the derivative of h we do know. It's 0. It's a constant. So we actually have everything we need. Now let's solve. So I'm going to cross multiply, make my life a little easier. So I get 12y minus x equals hy. This will get me distribute 12y minus 12x equals hy. Right, and now I can take a derivative, d of dt. Now let's talk about this again. So derivative of 12y will just be 12, but wrong variable, dy dt. Derivative here would be 12, wrong variable, dx dt. And then over here, right, you think, oh, it's product rule. Don't forget, h is a constant, right? So this is actually like taking a derivative of, like, I don't know, 2y. It'll just be 2. H is a constant here, so you just get h. H is a constant. Right, that was just an example. So that's the tough thing. You gotta like mentally wrap your mind around. H is just a number. We still know what the number is. So the derivative of hy is just h. Wrong variable. Almost forgot. dy dt. So we're there. Now all we gotta do is plug in everything we know. So I know dy dt equals 2 dx dt. So I can plug that in there, and then so everywhere the dy dt, I gotta plug into a 2 dx dt. So it's gonna be like this: 12 2 dx dt minus 12 dx dt equals h times 2 dx dt. Let's do some math on this. So I'm gonna get 24 dx dt, 24 dx dt minus 12 dx dt equals 2h dx dt. Just doing the math here, right? Subtract these, you get 12 dx dt equals 2h dx dt. I know it looks scary, but let's come and do math. What do we do next? Divide. Divide by dx dt. These cancel out, and you actually just end up with 12 equals 2x, or 2h, sorry, not 2x. Divide by 2. H equals 6, so he is 6 feet tall. Right? It's a little funky right there, but that's all we're doing. Taking all the derivative of that. You end up with dx dt, but luckily that cancels out, and all you're left with is 12 equals 2h. So h equals 6. 18. A 16-foot ladder is sliding down a wall. So let's draw that part of it. So here's my wall. Here's my ladder. Magnifique. Okay. Let h be the height of the top of the ladder. So this is from here to here is h. Sliding the top of the ladder against the wall at time t. Let x be the distance from the wall ladder's base. So here is x. Assume the bottom slides away at a rate of 3 feet per second. So the bottom sliding away, it's going this way. So my rate would be dx dt equals 3 feet per second. Find the velocity to the top of the ladder at time equals 2. So they want us to find dh dt. Time equals 2. Given if the bottom is 5 feet from the wall at time equals 0. So that's, we're going to actually use that later. But that's just kind of the general idea. So we have all this. Right, we have dh dt, dx dt. Now the ladder. Now here's the thing with the ladder. It's a ladder. It's a constant. It's not going to change. The ladder is its own height, which they tell us is 16. So there's our constant. So that's never changing, right? The ladder's always going to be 16 feet. We're just going to move around with it. So we need an equation that connects all these guys. Well, looks like a Pythagorean to me. So we're going to do x squared plus h squared equals 16 squared. Keep in mind, remember, 16 is a constant. That ladder is not changing. It's always going to be 16 feet. So we have this. Now, before, like I always like to try to do, what happens if I take a derivative of this? If I take a derivative of x squared, I get dx dt. Good, I have that. If I take a derivative of h squared, I get dh dt, which is what I want. So I'm all good. So let's take a derivative. So I'll get 2x dx dt because the wrong variable. Here I'll get 2h dh dt because the wrong variable. And don't forget the derivative of 16 is a constant, it's a number. So I just get 0, there's no variable there. So you just get 0 there. So I get that. So next we got to find out, we plug in what we have. So dx3 is 3. Told us. I want dh dt and I need x and h, which I don't have. But what do they tell us? That time equals 2. If the bottom is 5 feet from the wall, so the bottom of the ladder is 5 feet from the wall at time equals 0. How far is it at time equals 2? So we got to think about it logically again, right? At t equals 0, at time equals 5. And at every second, it does 3 feet. So, at time equals 1, we're 8 feet away. And at time equals 2, we're going to be 11 feet away. I can do math. Right? So every second, we're creating 3 feet. So, we start at 0. We start at 5 at t equals 0. So that means at 1, we're at 8. And at 2, we're at 11. So if we're trying to find these missing variables here, we're going to use the fact that they want us to find them at time equals 2. So we have a triangle here, where this is always 16. This is now 11. And I can use that to find out what the height is going to be. So we're going to do h squared plus 11 squared equals 16 squared. So h squared is going to equal the square root, h is going to equal the square root of 16 squared minus 11 squared, which would just be about 135. So that's what h equals, about 135. So let's go back to here, plug stuff in, get rid of the 2's again. X is 11, because remember, it's at 2 seconds. So at 2 seconds, we're actually 11 away. We start 5 away, but then we go 3 every second. So we're actually 11 away. This is 3. We just figured out h was, when this, at 2 seconds, that h is rad 135. And then dh dt is what we're looking for, equals 0. So let's move stuff aside. So I get 33 equals radical 135. Sorry, I moved it to the side, so negative 135 dh dt. Right, I moved this guy over, so it became a negative. So then you divide, and you get 33 over 135, negative 33. Or if you want, negative 2.840 feet per second. So there we go. So it slides down about, no, it's a negative because it's sliding down. In general, when you do an XY graph, sliding down should be negative, right should be positive. Sometimes it doesn't matter, but in general, down should be negative, right should be positive. And this is sliding down, so we have a negative force. Okay, last couple, they're all circular cones. They're all cones. So the next one, the radius of a right circular cone. of a fixed height equals 20 is increasing at a rate of 2 centimeters per second. How fast is the volume increasing when the radius is 10? So let's go through this. So right circular cone is fixed to a height of 20. It's increasing at a rate of 2 centimeters per second. The radius of a right circular cone of fixed height is increasing at a rate of 2 centimeters per second. So my radius is actually changing. So saying dr dt equals 2 centimeters per second. Alright, I'll think about that for a second. The radius of a right circular cone of a fixed height is increasing at a rate of 2 centimeters per second. So it's not like the other ones we're doing. We're just saying, like, here's a cone. I probably drew it too big. It's a fixed height, so height's 20. The radius is changing at a rate of 2 centimeters per second. So this is getting bigger. How fast is the volume increasing when R is 10? So they want to find dV dt when R is 10. So let's come up with an equation. Now we're just talking about the volume. So the volume of a cone, right, is 1/3 area of the base, pi r squared, times the height. Just like that. Now in this case, what happens if I take the derivative? I get dV dt, which is what I want, and I get dr dt, which is what I have, and I get dh dt. But I don't have dh dt, but it's a fixed height, so this is not changing. I can actually plug in 20 there, right? So if I would have done that, I was like, oh, I get dh dt. How do I don't have dh dt anywhere? So there's a problem there. In this case, it's an easy to fix because it is a fixed height, so I just plug in 20. So now my equation is this. And now I take a derivative, no problems. I get dV dt, which is what I want, and I get dr dt. So let's take a derivative with respect to t. 1, the wrong variable. Over here, bring the 2 down. Subtract 1 off, so I get 40/3 pi r. Don't forget, wrong variable. Now we can plug in what we know. I know dr dt is 2. And I know r, we want it at 10. So I get 20 times, so I get, what is that, 400 times 2, so I get 800/3 pi. And don't forget the units. It would be, we're talking about volume, so it's going to be centimeters per second. Centimeters cubed per second. There we go. Next one. Suppose that both the radius and the height of a circular cone changes at a rate of 2 centimeters per second. How fast is the volume of the cone increasing when R is 10? The height is 20. So it's similar to the last one. We have our cone here. Now what do they tell us? Suppose the radius and the height of a circular cone are changed at a rate of 2 centimeters per second. So the radius and the height are changing. So remember, changing means rate. Like they tell us rate. They gave it to us. So both of those are 2 centimeters per second. How fast is the volume of the cone increasing when R is 10 and H is 20? So they want us to know, what is dV dt when R is 10 and H is 20? So this is our given. This is our want. Like always, do we have an equation that connects all these? We do. It's volume equals 1/3 pi r squared times h. Now here's the part that you're not going to like. What happens when I take a derivative of this, right? Like I always check. Derivative v is dV dt. Good, I want that. How about r? dr dt. I have that. How about h? I actually have that. So in this case, there's actually not a problem having r and h there. I just have two variables because I have both of those values. So I can just take the derivative straight out. What happens when I do that? So let's take the derivative of both sides. Derivative v is 1, but wrong variable. Over here, I have two variables, so it's a product rule. So I'm going to combine these guys like this. Right? This will be my f, this will be my g. We got to do the product rule. F prime g plus g prime f. Right, again, there's two separate variables. So when it's two separate variables, I've got to do a product rule. So I'm just going to combine all these together because those are just numbers. So let's do the derivative of the first one, bring the 2 down, subtract 1 off. So I get 2/3 pi r. Don't forget, I took the derivative of r, and that's the wrong variable, so dr dt. And also don't forget you got times by the first one left alone, the second one left alone. So h plus, take derivative of this one, derivative of h is 1, but wrong variable, dht, times all that left alone, times all this guy left alone. So like that. So that's my derivative. And now to take a derivative, plug everything in. So what are we plugging in? dvdt is what I want. R is going to be 10. So R is 10, R is 10. H is going to be 20, so 20. And then dr and dh are both 2. So with this, we have 2/3 pi times 10 times 40 plus 2 times 1/3 pi times 100. If we simplify that, dv dt is an equal 100,000 pi, sorry, can't read. 1,000 pi, and then units, centimeters cubed over seconds. So like that. So we get all that. Okay, one more left. Last one. A water tank in the shape of a right cylinder. Oh, there we go, another cone. A cone radius 300 and a height of 500 leaks. So you have a cone. It's like an industrial size cone. The height is 500 and the radius is 300. And leaks water from the vertex at a rate of 10 centimeters per second. So we're dripping water here. So we're losing dv dt. Right, notice the units. If you're not sure, notice the units. It's first it's a rate, so that's why it's dv dt, not just like v or something. And also it's cubed, right? So volume. And we're losing, it's leaking water, so minus 10 centimeters cubed per second per minute. Find the way to which the water level is decreasing when it is 200. So they want us to find dh dt when h is 200. So that's the question. So like we always do, we'll set up an equation. Equation will be volume equals 1/3 pi r squared times height. Now like I always do, let's check to make sure when we take a derivative it's all going to work out. Right, derivative, we take a derivative of this, I get dv dt, negative 10, fine. Go over here. Derivative r is dr dt. We actually don't have a dr dt anywhere. So that's going to be a problem. I could get rid of my r. And then dht is what I'm looking for. So we got to do what we always do. Right? If I switch one of these, set up a proportion. Now I didn't draw it here, but since we're talking about water level, I should draw it. Here's our water level with its own radius and its own height. Right, so that's how we're going to set it up, because we're talking about the water level here. So it's draining, so it has its own r and its own h. So we're going to set up r over h is an equal 300 over 500. Right, this r over this h is equivalent, similar to this r over this h. These reduce, so I just get r over h equals 3 over 5. Again, I'm trying to solve for r because I want to plug in for r. So figure out what r equals. Times both sides by h. And r equals 3h over 5. So I can plug that into here. So I get this. Simplify a little bit. That goes both of them. I'm going to get 9 over 25 h squared. 9 over 25 times 1/3. The 9 and the 3 cancel out. I get 3. So I just have this. 3 over 25 pi h cubed. Right? H squared times h is h cubed. Now if I take a derivative, I'm going to get dv dt, which is what I have. I'll get dh dt, which is what I want. So I'm all good. Now we can take a derivative of this. So I get 1 dv dt. Bring it down, subtract 1 off. 9 over 25 pi h squared. But don't forget, wrong variable, dh dt. Now we can plug everything in. This guy is negative 10. Keep that in mind, right? We're losing water, so it should be negative. Equals 9 over 25 pi. H, they said they wanted it at 200 squared dHdt. So divide by all this because I don't get that out of the way. So I get negative 10 over 9 over 25 pi 200 squared equals dHdt. When you're doing your calculator, I would recommend either leaving it like this as your answer, that's fine, or doing all this in your calculator first and then doing 10 divided by that. I'm going to leave it like this because we're looking on late in the video. Those are the units, right? dH, so it's just normal centimeters over time, which in this case was minutes. So there we go. We are done.